So now we will start learning about the new method. So far, I mean, many of our proof is about expectation of certain random variable x. Then we show that this is alpha, so we can actually achieve, I mean, above alpha, I mean, at least alpha or at most alpha, and then we interpret what it means. So many times these are good enough. So far, the problems that we have dealt with, for that, I mean, this was good enough. But in also many times, I mean, just showing the existence of certain, I mean, case that this is at least alpha is not enough. So, for example, consider a case that there are several random variables, and we want to show that all of them are, I mean, close to alpha at the same time. If you simply, I mean, compute the expectation of x plus y plus g, and then showing that this is at least 3 alpha or at most 3 alpha, is not enough. In this case, I mean, what we actually want is that x is very close to alpha, say, I mean, 1 plus minus alpha. No, 1 plus minus, say, epsilon alpha, with the probability, say, 90%. And then y is also 1 plus minus alpha with 90%. And g is also 1 plus minus epsilon times alpha with 90%. Then we can actually conclude that with 70% probability, I mean, all 3 events happen. Here, if I write down 1 plus minus alpha times, I mean, 1 plus minus epsilon times alpha, this is a number between 1 minus alpha, 1 minus epsilon times alpha, and 1 plus epsilon times alpha. Some number between here, I will write it this way. Anyway, so this kind of suggests that when a random variable is given, and then we know its expectation, say alpha, it might be convenient if we can show that it's actually very close to its expectation with some probability which is close to 1. So in other words, what we want to show is that this random variable is here, and then we know its expectation. And somehow, if you, I mean, sample this x, if you choose this value x with this random variable, then its result is, I mean, between 0 and infinity, and here is alpha. And you randomly choose, I mean, some things, and then this x now has a value here and here. But we want to show that with some probability close to 1, it's very close to this alpha. If that happens, I mean, if we can somehow show that, then that's useful for us. In other words, I mean, this value of this random variable x is very concentrated around this alpha. That's what we want to show. So this is just a term we, I mean, called concentration. That means this is a phenomena that the random variable alpha is very close to its expectation with some high probability. So this is something that we want to show. For this to happen, again, the x must be very, I mean, distributed in the way that it's very concentrated on x. So in order to measure how concentrated this x is around its expectation, we need some concept which measures how spread out x is from its expectation. If it is more spread out, that means it has weak concentration, maybe no concentration. But if it is not so spread, then it has a strong concentration. However, we already learned something in probability theory in undergraduate or even in high school, which measures how spread out this random variable x is from its expectation, which is a variance. So we define this variance as some value which measures how spread out x is. So you take x and you subtract the expectation, and then you take square and then you measure the expectation of that. Here again we take the square here because if we don't take the square, then this has a positive value and negative value and they cancel out, so the entire thing becomes 0. So it doesn't measure anything. So by squaring it, we actually measures how much deviate x is from its expectation. Because when it's deviated from its average, its expectation, deviate towards upward or towards below to the downward doesn't really matter. Both are deviation. So by squaring it, we can actually measure it. And if you rewrite this formula, this is actually expectation of x squared minus expectation of x squared. So you see the difference. The square is inside the expectation and outside expectation. Here, this is not difficult as we just compute the expectation as we did before, and then we just square it. Then you get this number. So in order to measure the variance, in order to compute the variance, the essential part is this part. And this part is what's called second moment. So we say this is, for random variable, this is first moment, second moment, third moment, fourth moment, and KAIST moment. You take the square on itself. So study about variance is called second moment method because we essentially have to study about the expectation of x squared. In many cases, when a random variable x is given, we sometimes write mu as its expectation and sigma squared as a variance of this. So we want to collect some theorem which connects the variance and the concentration. For that, let's collect one well-known inequality, which is Markov inequality. So when x is a random variable which takes a non-negative value, non-negative random variable, and say a is some number bigger than 0, then what we know is the probability that this x is bigger than a is at most the expectation of x over a. This can be easily seen because expectation of x is what? This is essentially, let's just consider the discrete case. So as we will not rigorously prove it, let's just consider the discrete case that this x takes the value of non-negative integer. Then this is t times the probability of x equal t. And this is actually bigger if you truncate this value. Here, this is a times probability x is, t. You just delete the initial term. And then here t is at least a. So this is bigger than or equal to a times probability that x is at least a. So you divide both sides by a, then you get exactly this inequality. And even if x has a non-integer value, it could be have other value, you just change this summation into integral, and then you can easily show this. So we will not prove it rigorously, but this gives you an idea why this Markov inequality is true. And by using that, we can actually show this basic Chebyshev's inequality, which shows concentration result for given variance. So when x is given, and again sigma square is this variance, so sigma is square root of variance. For any lambda, the probability that x is deviated from its expectation, its mean, average, or whatever you call this is expectation, by lambda times sigma is at most 1 over lambda square. So it's, you can take lambda a bit big, then you can make this small. So as long as this sigma is small, then this x is more or less mu plus minus lambda sigma. So if this is smaller, compared to mu, then this is x is very close to mu. So we can show that x is very close to mu as long as this sigma is small enough, and this measures how concentrated it is. And the proof is easy because sigma square is the variance, and this variance is same as the expectation of x minus mu square. And we apply the Markov inequality. Then, what do we know? Markov inequality, you just, let's say, you just multiply a on here, then this is expectation and this here. This is lambda square, mu square, probability that the x minus mu is bigger than lambda sigma. So this is same as the probability that the x minus mu square is at least lambda sigma square square. So by rewriting it this way, you get this. Now you just divide the both sides by these. You get the 1 over lambda square is upper bound of this. So this finishes the proof of Chebyshev's inequality. So now we want to, so second moment method is, as I mentioned before, about measuring this. So once you measure this, you get variance. And then with variance, you apply this to show concentration. That's usually called the second moment method. And this Chebyshev inequality is actually best possible because if you consider the random variable, which takes three values, either mu or mu plus lambda sigma or mu minus lambda sigma with the probability 1 minus 1 over lambda square, 1 over 2 lambda square, 1 over 2 lambda square. So which sums up to 1. So if you consider this random variable, then you can actually show that this cannot be further improved. So this is best possible. But this is two special random variable. So for certain random variable which satisfy certain good property, we can actually improve this further. So that's what we will also study later. So for now, but we are happy with this Chebyshev inequality, and we see how one can actually use this. And just like before, many cases, we want to consider the random variable, which is summation of a simpler random variable. And simpler is the indicator random variable in most of the time, but let's just say, yeah, it's a summation of simpler random variable. So in order to measure the variance of X, it's a convenience if we can also somehow find some, formula here based on each xi. So what's variance of X? This is the expectation of x squared minus expectation of x squared. And what's this? This is expectation of summation of xi, xj, I, j between m. So that's, you take this and then you squared it, then this is what you get. And then here is that this is same as summation of expectation of xi. You take the square, so summation of expectation of xi, expectation of xj, I, j in m. And what do we know? We know that variance of xi is same as expectation of xi squared minus expectation of xi squared. You collect the terms where I and j coincide, then you get the variance of xi and plus summation of expectation of xi, expectation of xij, xi times xi, xi times xj minus expectation of xi, expectation of xj. So, as we assume that each xi is simpler random variable, so this may be easier to compute than x and variance of x, and this also may be, easier to compute than the directly computing variance of x. So we give some name on here. So we write this as sum of the variance of xi plus covariance of xi, xj. So we say that the two random variable y, g are given. We define its covariance as the expectation of yg minus expectation of y times expectation of g. So we will, so typical technique we will use is that we want to measure the variance and use this Chebyshev inequality to show concentration. For that, we need to, compute the variance. And in many cases, x is a summation of simpler random variable. And for each random variable, we compute its variance. And we compute its covariance. In many cases, we want to show that this covariance is small, so we can almost neglect it. Then this gives us essentially the variance. And we want to apply Chebyshev to solve the problem. So that's roughly, what we do in second moment method. So in next video, let's consider an application.